Okay, so moving on with some more theorems and facts and observations and examples on sequences. So here are some more. So theorem, very useful little fact. So let's divide it into two parts. The nth root of n, this is a specific sequence, and the limit of this as n goes to infinity, does anybody know? Right, the answer is 1. And getting intuition for this is not necessarily immediate. One way to get intuition is to start plugging in values. Okay, so the first element is, the first root of something is just a something. So the first element is 1. The second element is root 2, right, which is something about 1.4, right? Then you have the third root of 3, then the fourth root of 4. You can plug in a few more into the computer, and that's one way of getting intuition. This requires proof. Okay, saying that this is true requires proof, and I'm not going to prove this. Okay, but it's very useful. Okay? Here's another one. The nth root of a constant goes to 1 as n goes to infinity for any positive c. Any constant. So if you take 2, root 2, third root of 2, fourth root of 2, fifth root of 2, that's going to converge to 1 as well. Okay? So maybe an example, suppose I ask you, suppose I asked you what is the limit of the sequence an, which is the nth root of 3 to the power 2n plus 1 times n. What's the limit of this thing? And remember, when you have n's all over the place, I see 3 of them here, you can't just do them one at a time. Okay, you have to somehow handle this at once. The arrow n goes to infinity can only appear once. Okay? So what do you do with something like this? Well, you can rewrite it as, so 3 to the power 2n plus 1 is 3 to the power 2n times 3 to the power 1. Do you agree? And 3 to the power 2n is the same as 9 to the power n. Do you agree? So do you agree that I can rewrite this as the nth root of 9 to the power n times the nth root of 3 times the nth root of n? Do you agree that this and this is the same thing? Yes? Okay. What's the nth root of 9 to the power n? Okay. Okay. So it's 9 times the nth root of 3 times the nth root of n. This goes to 1 by this theorem. This goes to 1 by this theorem. Therefore, the product by limit arithmetics goes to 9 times 1 times 1. 911. I can hear the sirens. No, just kidding. Okay. Good? Questions? Okay. Some more. So, theorem. Suppose that an is a non-negative sequence. Okay, so all the ANs are non-negative, and converges to L. What can you say about L? Right. L is also going to be non-negative. If you have a sequence of non-negative numbers that converges, the limit can't suddenly be negative. Do you agree to this? Does it make sense? Okay. Let's call this 1. 2 is going to be generalizing 1, generalization of 1. Suppose that an is greater than or equal to bn. And that the limit of bn is some k, as n goes to infinity, and that the limit of an is L as n goes to infinity. Then, what can you say about the limits? Not bigger. Right. So, L is greater than or equal to K. Do you see that theorem number 1 is a special case of theorem number 2? Just take the bn's to be 0. Do you agree? Okay. Remarks. So the first remark is, and we said this, we had an analogous version of this for functions, and we said this remark when we discussed the similar statement for functions. Not true if we replace less than or equal with strict inequality. So what do I mean by this? I mean that if, let's take number 1 for example, this remark is true for both of this. So it's not one not, this is remark number 1. So let's call it remark A. Both of them are not true if we replace the inequalities with strict inequalities. Why? Suppose you have a sequence that is strictly positive. All the elements are strictly positive. Does it imply, and it converges, does it imply that the limit is strictly positive? Give me a counter example. Very good, very good. So counter example. 1 over n is a strictly positive sequence, but it converges to 0, which is, of course, not strictly positive. Okay? So this is again a situation where some form of statement about inequalities is no longer valid when you make when you make them strict. We're going to see many of these throughout the course. That's always a point of delicacy, always a point where you have to be careful when you want to change statements about strict inequalities to statements about inequalities to strict inequalities. So that's one remark. Another remark still true. So both statements do remain true if instead of requiring that, for example, an is greater than or equal to 0, when I write something like this, it means that for any n, all the ans, all the elements are non-negative. Okay? What can I replace? How can I loosen up a bit and still have it remain true?
The limit is greater than 0?
That's the statement about the limit. But I'm asking, can I relax this requirement a bit? So what I mean is, I can require this to hold only from a certain n and onwards. We said that in the previous hour. So they're still true if we require for example, an greater than or equal to 0, not for any n, but for n greater than some n. So if the first 17,000 elements are negative, but starting from there, everybody's non-negative, this statement is still going to be true. Do you agree? If you have 17,000 elements which are negative, and then everybody's positive, the limit is going to be positive or non-negative. Do you agree? So that's the second remark. And the third remark, or maybe let's make the third remark into a theorem in its own right. Theorem. If an converges to L, Bn converges to K, and L is greater than K. Okay, so this is kind of a different direction of those theorems. So now I'm assuming that both sequences converge, and I assume that I know how the limits relate. So L is greater than K. What can I say? Then,
The n is bigger than a.
right, then the ANs are going to be bigger than the BNs. Is that going to be true for any n?
No, we said that it cannot be changed with a strictly.
No, but this is a different theorem.
Is it n goes to infinity?
Yeah, it's always n goes to infinity. Always.
Only after a certain big.
Right. Then AN is greater than BN for n greater than some big N. Okay? Let's think why this makes sense. Let's think for a minute why this makes sense. Well, just a quick drawing. Here's L, which is the bigger one, O. Here's K, and here's L. This is just the idea of the proof. Okay, I'm not going to completely formalize it, just the idea. What does it mean? What does it mean that AN converges to L? It means that eventually, starting from a certain index and onwards, if I take a small neighborhood of L, all these ANs are going to be here, right? That's the definition of the limit. Take epsilon. If you go far enough in the indices, all the elements, their distance from L is going to be less than epsilon. Do you agree? So from a certain point onwards, all the ANs are going to be here. ANs here eventually. So maybe there could be some of them that are outside, right? But from a certain point onwards, they're going to all concentrate here. Do you agree? One second, I see your question. 1 second. What about the BNs? The BNs converge to K, so if you take a small neighborhood of K, the BNs are eventually all going to be here. So the BNs eventually here. This eventually means that maybe the first 17,000 of them, there's an AN here, and an AN here, and a BN here, and another one here, and maybe one all the way down there. But eventually, the ANs concentrate here, and the BNs concentrate here. L is greater than K. Eventually, the ANs are all going to be bigger than the BNs. This eventually is what I mean by for n greater than some fixed n. Is this clear? Is the idea clear? Does it make sense? In fact, this is precisely the proof. You just have to write it very carefully. But this is really the proof. It's not, like an idea and the proof being something completely different. This is the proof. It's just stated a bit intuitively and not completely formally. Okay, so this is idea of proof. Question? Yes?
So for theorem number 2 over there,
Theorem number 2 over here, yup.
there also be n greater than big N. There also.
Here? Yeah. This remark, be here, implies to both of them, to both 1 and 2. So what I want to do now is move on to sequences that go to infinity. Now, this is somewhat tricky terminology-wise. Some people would say, some references would say, that if a sequence does not have a finite limit, then it diverges. And it can either diverge like -1, 1, or it can diverge to infinity. Okay? Do you see that those are two very different situations? Diverging because it just doesn't have a limit, it bounces back and forth, and diverging because it diverges to infinity. Okay? And other references would say that it converges to infinity. Because infinity is a limit, and they would say it converges to infinity rather than diverges to infinity. That's just terminology. Okay, so don't let the terminology confuse you. The notions themselves are very clear. It can have a finite limit, it can diverge in the sense of not having a limit at all, or it can, and let's just say, go to infinity, and that's what I want to define now. Okay, you can call it diverge to infinity or converge to infinity, and I've heard both. Okay, so let me put some of these aside. Okay, so definition. And this should not be surprising to you. It's again going to be very similar to the definition for functions. We say that, and I'm just going to write it so I don't have to use diverge or converge, that the limit of an is infinity if, and now instead of epsilon, we're going to have this big M. If for every M, there exists an N such that if you went beyond N in the indices, then the elements of the sequence went beyond M, got closer and closer to infinity. Okay? And a similar definition for the limit being minus infinity, you would just replace this by less than. Okay? Okay, examples. Examples. So, an example would be n factorial. Do you agree that this goes to infinity? As n gets bigger and bigger, the sequence gets bigger and bigger. If you want to exceed 7,000, you need to find from which element onwards everybody's bigger than 7,000. Do you see that? Is my talking, even though it became a bit fast, is it clear? Is it falling on good. I see all the heads now nod. I'm happy. Okay. Another example, an equals 2 to the n. True? Okay. Another example, an equals n to the power 3. Okay, so all these exponential ones when this is positive, and on all these polynomial ones when this is positive, they're all good? Okay. Can you give me an example which, so all of these satisfy that the limit is infinity? Can you give me an example of a sequence, listen to this, a sequence which is not bounded, but doesn't go to infinity. Not bounded. Of course, if it's bounded, it's not going to go to infinity, right? That's easy. All the sequences that have finite limits or that just diverge like -1, 1, of course, don't go to infinity. But can you give me an example of a sequence that is not bounded, but does not go to infinity? Yes?
And +1 over n squared.
Why? Okay, so don't just throw guesses. Try to build up an example that you can maybe argue why it would be true.
What negative
Hmm?
What negative
No. Okay. So let me rephrase the question. A sequence which is not bounded and doesn't go to infinity or to negative infinity. Okay.
Is it number or
I would guess not. Not.
The you can use Differential here?
Not functions.
Yeah, I know, but you can say that an is equal to, say, the whole statement that you said with the Differential function?
Well, Differential function is something that is defined for any real number. A sequence is only defined for natural numbers. So what is the first element of your sequence? Differential was just ones and zeros, right? So it's not clear. Here's an example. That's very bounded. What I'm trying to okay, so let me wave my hands and then we can find a formula for it. I want a sequence that's not bounded, so the elements are going to have to get bigger and bigger or smaller and smaller, but I want it not to go to infinity and not to go not to go to infinity and not to go to negative infinity. I'm confused now.
Yeah.
Okay, so I want it to kind of bounce back and forth, but still get bigger and bigger and bigger and bigger. I'm out of the screen, but okay. So here's an example. -1 to the power n times n. This sequence is the sequence -1, 2, -3, 4, -5, 6, -7, 8. Do you see that? It's clearly not bounded. The elements get as big as you want and as small as you want, but it doesn't converge or diverge to infinity or to negative infinity. Do you agree? Everybody? So this is not bounded, but the limit, so let's call it an, but limit an is not infinity and is not negative infinity. Okay, it doesn't have a limit. Has no limit. Does everybody agree? Is this clear? Okay? Okay. Good. So those were some examples. And what's the challenging issue about infinite limits, just like with functions? Do you remember? Why do we separate this? Why don't we just throw it all into the same basket? Right. The theorems that we had, even limit arithmetics, don't hold for infinity. Okay? So we said that for functions. Let's say it again now for sequences. An issue that's very confusing to many people. This course is fast. The pace is fast. And we studied functions, and then whoop, now we're studying a totally different creature, sequences, and next week we're back to functions, and it confuses. Okay, so you have to somehow, I don't know, focus and be careful, and it's hard. It's not easy. And one thing that confuses many people is taking functions as examples for sequences and sequences for examples as examples for functions. And that happened like 3 or 4 times just today in this class, and it happens a lot. And you just have to be careful. It's just a word of caution. Be careful. It doesn't make sense to say that the Dirichlet function is a sequence. It doesn't compile. And if it comes to mind, then maybe it's not wrong. Maybe there's an idea there that somehow crept into your intuition. But be careful. Just remember, the Dirichlet function is a function. If you want to somehow put your hand on a property that it has and translate that into sequences, then just remember you have to do that. Okay? So for example, in this case, the Dirichlet function, which is a very good counterexample to many things in functions, in terms of sequences, well, it just takes values 1s and 0s. I don't know exactly how you can make it into a sequence, but as a sequence, many of its phenomena are going to kind of disappear, vapor out. It's just 1s and 0s, right? So, not saying that you weren't onto the right thing. Maybe you were, but you have to be careful. And I'm saying this because it's a very common sort of point of confusion. Functions and sequences. Okay? Okay. So, key issue. No limit arithmetics. Well, not exactly no limit arithmetics. Some we do have. Limit arithmetics do not hold in general. So for examples, so suppose we take the sequence n squared minus 1 divided by 3n squared. Do you agree that this is a situation of, okay, so this is example 1. This is a situation of infinity over infinity. The top goes to infinity, the bottom goes to infinity. But the limit is not 1. Infinity over infinity is not 1. Why? What is the limit of this thing? Right, because let's divide top and bottom by n, so it's 1 minus 1 over n squared divided by 3, and as n goes to infinity, this converges to 1/3. Do you agree? Everybody? Another example, this one we're going to discuss further. 1 plus 1 over n to the power n. So, do you agree that this is of the form, the stuff inside the parentheses goes to 1, because 1 over n goes to 0. So this is of the form 1 to the power infinity. Do you agree? Yes?
Yes.
But the limit of this thing, so you would guess that the limit is 1, right? But the limit of this thing, does anybody know?
E.
Right, you're right, is e. E is a number which is 2.71 something. Okay? And we're going to discuss this example and argue why it's e later on. Okay? So it's not true to say that 1 to the power infinity is just 1. Here's a counterexample. Clear? And maybe this is a good point to remark, to kind of show how you can get things very, very wrong if you go to the limit in steps. So I can say, okay, 1 over n goes to 0, right? So this goes to, as n goes to infinity, 1 to the power n, because this goes to 1. And then 1 to any power is just 1, so as n goes to infinity, this goes to 1. And I've seen many people write this, and maybe you're looking at it and thinking, hey, that makes sense. Okay? It's wrong. You cannot take n's to infinity one at a time. Here I took this n to infinity, left this n, even though n went to infinity, but this n somehow escaped the going to infinity, and then I did it again for this n. That's wrong. That's false. And we're going to prove that, in fact, this does not go to 1, it goes to e. Okay? So this is a big, big, big no-no. Okay? So this is not true. You can't go to infinity and leave some of the ends for later. Is this remark clear? Okay? So, beware.
If the problem was just 1 to the power of n goes to when n goes to infinity.
If it was just this,
It's still not 1, right?
no, 1 to the power n, it goes to 1, because 1 to the power n is another way of writing just ones. What is this sequence? This is the sequence. What's its first element?
1.
What's its second element?
1.
Third element? This is just the sequence 1, 1, 1, 1, 1, 1, 1. So this part of it is true. Okay? This is true. When I write this, I mean something that goes to 1 to the power of something that goes to infinity. This is not something that goes to 1, this is just 1. This is something that goes to 1 to the power of something that goes to infinity. Clear? Everybody with me? Okay. Another example, maybe n to the power 3 minus 1000 n squared. Do you agree that this is a situation of infinity minus infinity? This goes to infinity, this goes to infinity. Do you agree? Is it true that this goes to 0?
No.
No, very not true. What does this go to? What's your intuition? Infinity, right? The n cubed is going to beat 1000 n squared for very big n's, right? And a formal way of writing it is to pull out an n squared here and leave n minus 1000 here. And then n minus 1000 goes to infinity, n squared goes to infinity, and this goes to infinity. And that's an example for one limit arithmetic that does hold. So infinity times infinity is infinity. Okay, clear? Okay, we discussed these for functions. We had several examples there. I think they were kind of different, but the same ideas. Okay, so whenever we have these situations where we have infinities, we have to be careful. We can't just do arithmetics. That's just not true. Okay? Okay. A couple of theorems. Okay. So, theorems, these are very, very basic. Their proof is very elementary from the definition. If you want to have some practice, you can try them. Okay? I'm not going to prove them because we're not going to, as I said several times, we're not going to be asking you to prove things with the definition, at least not this semester. But These are good practices if you want. So if an goes to infinity, this implies that 1 over an goes to what? To 0. Does everybody agree with this intuitively? Does it make sense? Right? It's very, very intuitive. If you make the denominator bigger and bigger and bigger, then 1 over it is going to go to 0. Right?
Yeah.
Okay, so let's call this 1. 2. If an goes to 0, then 1 over an goes to what? Infinity. Do you agree? Everybody?
Can also go to negative.
Very good. This is false. This is not true. Why? Because saying that an goes to 0, the an's can be some negative and some positive. For example, if all the an's are negative, then 1 over an is also going to be negative. It's going to get bigger and bigger and bigger, but the limit is going to be minus infinity. Do you see that? Okay? So just the way it's written, it's false. It's not a true statement. If you want to make it true, you can, for example, add, suppose the an's are greater than 0. And here we need it to be for every n because we're dividing by it. So if you have a positive sequence that goes to 0, like 1 over n, then 1 over it is going to go to infinity.
What about absolute value?
What do you mean, what about absolute value?
Give us an actual value.
You can say that 1 over an in absolute value goes to infinity. That would be a different way to correct this into a theorem. But the way it was written, it was not a theorem, it was false.
You say why it has to be for every n and not for n greater.
Well, just because I'm dividing by it.
You just wrote.
Oh, you're asking, okay, what I mean is that it can't be 0.
They're not that for every n.
Yeah, I understand, but what I mean, okay,
For every n that
they can't be 0 because I'm dividing by them.
n.
But you're right. If the first 17,000 are, why am I stuck with that 17,000 number? I don't know. But maybe I'm going to win the lottery for 17,000. Nah, that's not a lot. Okay. Anyway, the first 17,000 could be negative, and the statement would still be true. So you can add for any n greater than n as long as they're not 0. Okay. And what you suggested is a different way of making this into a theorem, which would also be true.
But can you just route that and then say goes to positive or negative infinity? Is that also what you're
No, because you can't drop this and then say the limit is either infinity or negative infinity. It can be neither. That's the example that we gave of a sequence that's not bounded but bounces back and forth between infinity and negative infinity. Okay, so that you can't say. Okay. Yeah, and maybe just one last theorem. The Sandwich Theorem. If an is greater than or equal to bn, this is the Sandwich Theorem at infinity. We don't need a third sequence. And the limit of bn is infinity. Then, what can we say? Right, then the limit of an's is infinity. Do you agree?
the sandwich, you wouldn't have to have one on the other side.
Well, not when it's infinity. That's exactly the point. You don't need it to be smaller than something that goes to infinity. If bn goes to infinity, and all the elements are bigger, that's it. They're forced to go to infinity. Do you agree? Okay, good. So, I guess we're going to... let's call it a day here. We still have not that short discussion of sequences, especially regarding monotone sequences and things following from there, and then we're going to discuss subsequences and then at some point we'll be back to functions. All these sequence business is auxiliary stuff in this course for our discussion of functions. That's the real thing we're interested in. Okay, so thank you.